So just to recall, when we want to factor a number such as 280, there are many different possibilities. Of course, if 280 were a prime, we would be finished, but if it's not a prime, then we can always write, by definition, write it as a product of two smaller integers. And we can do that in many ways. We could write it as 4 times 70, as 10 times 28, 7 times 40, and so on. And then we keep factorising down the tree. So in the first case we had here, 280 went into 4 times 70. 4 in turn, we can continue to further factor, 2 times 2. 70 we can factor into two integers in a variety of ways, but suppose we choose 7 times 10. And then the 2 and the 2, of course, we can't factor any further because they're primes, and the 7 is a prime, and then 10 is 2 times 5. And if we do other factorisation trees, we still end up with the same result in the end, which is 2 cubed times 5 times 7. Is this always the case? Is it possible that, say, for very large integers, perhaps there will be more than one prime factorisation possibility? So at this point I want to recommend to you a book written in 1945 by a very eminent mathematician, George Polya. It's called How to Solve It, and it's a classic. And in fact you can download it legitimately, I believe, as a PDF file on the net. I recommend it highly. And one of his suggestions was that if you can't solve a problem, then you look for a simpler problem which maybe you can solve. And then you bootstrap yourself back up from the simpler case to the more complicated case. And of course, if you can't solve the simpler problem, then maybe you should go to an even simpler problem until you come to something you can solve, and then you bootstrap yourself up again, as it were. So in this particular case, the special problem is going to be the following. If we have 4 primes, P, Q, R and S, and suppose PQ equals RS. In other words, suppose we have an integer which can be factored into primes in two different ways, P times Q and R times S. So that's a very special case of our problem. And the question is it the situation then that P is equal to R, and then in which case Q is S, or is it the case that P equals S and Q equals R? Are they the only two possibilities? And indeed, that will be the case, and we will prove it. But first of all, we have a related problem, and that is, suppose P divides just a product of numbers. So here, P of course divides PQ, and therefore it divides RS. So let's consider this problem. If P divides AB, we won't necessarily assume they're primes at this case, then is it the case that P divides A or P divides B? We will see that indeed P divides A or P divides B in this case. And we call the result the prime divisor theorem. In other words, if a prime divides a product of two integers, then the prime must divide at least one of them. The solution of the special problem will follow from this, and I'll go through the argument later, but briefly it's essentially nothing more than just observing that from here, if PQ equals RS, then P obviously divides PQ, and then by equality P must divide RS, and so by the prime divisor theorem we have that either P divides R or P divides S. But if one prime P divides another prime R, then the two primes must be equal. So we have essentially the result of the special problem.